Today we'll be covering 7-segment display interface, which is the first interfacing we'll be discussing in this unit 5. So, 7-segment display interface, it is an output device which is used for displaying alphanumeric characters. This is the purpose of using 7-segment display interface. And what it contains, it is 8 LED segments which are arranged in special form. So this is how the 7 segments are arranged in a 7-segment display interface. This is how we are naming the segments. The first segment is named as A, next B, C, D, E, F, G, and this dot what you are finding, this can be named as H bit. Okay, and out of these 8 LED segments, 7 segments will be using for displaying alphanumeric characters, and one segment, that is H bit, what I told, that will be used for representing decimal point in decimal number display. So 7 segments for displaying either the digit or the character. In general, we can say alphanumeric character. These are the 7 segments we'll be using for displaying. And this dot, that is the H bit, we can use for representing decimal point in decimal number display. There are two configurations in which 7-segment display comes. The two different configurations are common anode type 7-segment display interface and common cathode type 7-segment display interface. Okay. So what do you mean by common anode type and common cathode type is, so if you want to make a particular segment glow, if it were to be common anode type 7-segment display interface you are using, then if a particular segment need to glow means you need to send out a 0. Okay, so for that bit the value must be 0, bit value must be 0 to be sent, so that particular segment will be glowing. Vice versa operation in case of common cathode type 7-segment display operation. So whichever segment you want to make it glow, you need to send out 1 to that bit status. Other bits, whichever you don't want to make it glow, you need to send the status as 0. This is in case of common cathode type. So common anode type 7-segment display interface, it is vice versa operation. The segments to be glowing, their values must be 0. Okay. The other bits which you don't want to glow, make it glow, then you need to send the value as 1. Okay, so that we shall illustrate with an example. And one more point you need to remember is, whenever you want to display anything onto the 7-segment display interface, you need to construct a 7-segment code. It is an 8-bit code or byte code, you can say, that is to be constructed. So depending on what character you want to display onto the 7-segment display, or what digit you want to display, or what information you want to display onto the 7-segment display interface, depending on that, prior only you need to construct a 7-segment code for all those characters which are to be displayed, and that 7-segment code you need to send out, okay, to the 7-segment display interface, so that it gets displayed on that interface. So this is what you have to do. So what you have to send, so for a 7-segment display interface to display any alphanumeric character, you need to send a 7-segment code. So now in this slide, what we are seeing is how actually we can construct 7-segment code. So here we shall assume it is common anode type 7-segment display interface, and we shall try to construct a 7-segment code for displaying a digit. Okay. So in this table, it shows the construction of 7-segment code to display 3 on the common anode type 7-segment display interface. So what is that table that we'll see here? Just observe which are the segments to be glowing in to display 3, digit 3. You can see in the diagram, it is A, B, C, D and G. Only these segments must be glowing to display 3 on the 7-segment display interface. So just go for writing those 8 bits. So taking H as the most significant bit, the 7-segment code is constructed here in this example. H, G, F, E, D, C, B, A. So 8 bits are written, and whichever segment you want to make it glow, just take that bit status as 0, rest other bits as 1. Okay. So just observe here, I don't want to that is make H segment glow, that H bit, that dot what you are seeing in that 7-segment display interface. That's why H bit status is taken as 1. G should be glowing. See, A, B, C, D, G. Only these segments must glow. That's why their bit status is taken as 0. Okay. So what is this 8-bit code you have got, or the byte code, 7-segment code you have got? So the 7-segment code which we have constructed to display 3 is 0xB0. Okay, B0H is the hexadecimal code that is constructed. So 1011 means it is B, 0000 means it is 0. Okay, and it is left to you. It's left to your implementation whether you want to construct the 7 segment code considering H as the most significant bit, H to A, you can take the bits, or from A to H. You can see in this next table. See, A as most significant bit I have taken, and H as the least significant bit I have considered. And what is the 7 segment code you'll get for this? If you're taking this bit pattern, the 7 segment code to display 3 will be, it is 0x0d, 1101, 0000, it is hexadecimal 0, 1101, it is d. Are you getting? 7 segment code has to be constructed to display anything onto the 7 segment display interface. Whatever the constructed code you are having, you are going to send to the 7 segment display interface to display it onto that display interface. And it is left to you whether you want to take H as the most significant bit or A as the most significant bit. Any one convention you follow. Don't mix both. So any one convention you follow. Whatever the data you want to display, take everything with H as MSB and A as LSB, or do vice versa for all the data whatever you want to display onto the 7 segment display interface. So as an example, I've taken digit 3 and we have constructed the 7 segment code for displaying 3 onto this display interface. So what is the code? If H has MSB and A has LSB, if you are taking, it is B0H, the 7 segment code constructed. If you are taking A as most significant bit and H as least significant bit, it is 0DH, the 7 segment code constructed. Hope this is clear how to uh, generate the 7 segment code. Okay, and it is common anode type we are considering, since for your whatever the component you are having in the lab, it is having common anode type 7 segment display. So that's why whichever segment you want to make it low, its bit status you have to take it as 0, and whichever segment you don't want to make it low, you will be taking its status as 1. Okay, hope this is clear how to construct the 7 segment code considering H as MSB, A as LSB, or A as MSB and H as LSB. So in the lab syllabus programs, I have taken this convention to construct the 7 segment code. That is H as the MSB and A as LSB. So all the 7 segment codes, whatever we have constructed, this convention, first table information, what you are seeing, that convention is followed. Okay. Now we shall see the 4-digit 7 segment display interface, and any question given on 7 segment display interface. This is what the theory question you can expect. With a neat block diagram, explain 4-digit 7 segment display interface. So you need to write this 4-digit 7 segment display interface with this circuitry. This is just a block diagram, and you can explain. So 4-digit 7 segment you find, and how actually you are going to make LPC2148 microcontroller to communicate with the 4-digit 7 segment display interface. So from programmer's perspective, whatever is required, only that we'll be discussing. Okay. So here it is a 4-digit 7 segment display interface, and in this is what you are seeing in this diagram, and it is we are assuming this as common anode type. And if you want, since it is common anode type, whichever segment you want to make it flow, so bit value 0 we have to consider. To turn off any particular segment, we'll consider bit value 1. Okay, so that's what you need to know here. And you can observe 74164, it is actually serial in parallel out shift register, which is used for sending 8 bit of data to the 7 segment display. So 8 bit data means if I want to display one digit or one character onto one of the 7 segment display interface, totally 8 bits I have to send. Okay, so it is bit by bit we are sending the data. So one byte code, that is 7 segment code, is actually a byte code. One byte data how we are sending to the 7 segment display interface, it is bit by bit. Okay, and remember, always you have to send H bit first. So this is the order in which you need to send the bits. Whether you have constructed the 7 segment code considering H as the MSB and A as the LSB, or A as the MSB and H as the LSB, whatever the convention you have followed to construct the 7 segment code, what is the bit you have to send first? It is the H bit. H you need to send, then G bit, then F bit, then E, then D, C, B, A. So this is the order you need to send the bits. After sending 8 bits, then only you see the character in one of the 7, that is in the least significant 7 segment display unit, that character will appear. So since the bits are to be shifted, so the serial in parallel out shift register is used for sending the bits to the 7 segment, for shifting the bits in the 7 segment display interface. After 8 bits are sent, you will see one character in the least significant 7 segment display interface. So if you send one again 8 more bits to the 7 segment display interface, so whatever the character that was displayed in the least significant 7 segment display interface, that will be shifted to the next 7 segment display, and the new character will appear in the least significant 7 segment display interface. So if I want to send 1, 2, 3, 4 to the 7 segment display interface, you can see in this diagram. Okay. So assume I want to send out 1, 2, 3, 4 to the 4-digit 7 segment display interface. How we are going to send it out? So first we need to send the 7 segment code of 1, that will appear in the least significant 7 segment display. Okay, and then I need to send the 7 segment code of 2. So 1 will be shifted to the next higher 7 segment display, and 2 will appear in the least significant 7 segment display. Then I need to send out the 7 segment code of 3. So 1 gets shifted to the next higher 7 segment display, 2 will be shifted here, 3 will appear here. And finally, if I want to send 4, after sending 4, 1 gets shifted to the most significant 7 segment display, 2 will be shifted here, 3 will be shifted here, and 4 will be shifted here. So how many bits I need to send to display 1, 2, 3, 4 onto the 7 segment display interface? For each character or for each digit, 8 bits are to be sent. So totally how many bits I have to send is 34 bits. But if you send 8 into 4, since it is a 4-digit 7 segment display interface, 34 bits I have to send to the 7 segment display interface, so that after sending 34 bits, this is what the data you see on the 7 segment display interface: 1, 2, 3, 4. Okay. If this is what the data you want to see on the 7 segment display interface, which character or which digit you have to send first? So see 1, 2, 3, 4 are the digits I want to see. First I have sent 1, then I have sent 2, then I have sent 3, then I have sent 4. It is not just 1, 2, 3, 4 we are sending. To display 1, 2, 3, 4, what is to be constructed? It is 7 segment code. So on the right hand side, what you are seeing is this is just a declaration and initialization statement written in C. What you are seeing within pair of flower bases, this is an array. Data is an array which consists of 7 segment code constructed for 1, 2, 3, 4. So F9H is a 7 segment code constructed for 1, A4H is a 7 segment code constructed for 2, B0H, which we have already seen, this is a 7 segment code for displaying 3, 99H is a 7 segment code to display 4. Okay, so this is how you need to construct the 7 segment code, and just observe in what order I have initialized the 7 segment code: 1, 2, 3, 4. So, if you just consider in this order, if you send that data, there's a 7 segment code in this order, then only you'll see 1, 2, 3, 4 in the 4-digit 7 segment display interface. So the last diagram what you are seeing, so if you want to see this output, this is the order in which you are going to initialize the 7 segment code in the memory. Okay, so here in the diagram you can see and observe here which port is used as an output port for communication between LPC 2148 and the 7 segment display interface. So it is port 0 being used in this 7 segment display interface. Port 1 is not used, and it is serial in parallel out shift register used to shifting the bits, or to for shifting the bits, individual bits within the 7 segment display interface. It is port 0.15. Okay, 15th bit of port 0 is used to send, it is just one pin in port 0. This pin is used to send the data bit by bit. So if one character or one digit is to be sent, so you will be constructing 8-bit 7 segment code, and you know in which order you have to send out the bits: H bit first, then G, F, E, D, C, B, A. That is the order. And each bit you are going to send out through port 0.15. Only this pin is used to send bit by bit the data. And after you send each bit, you need to apply the clock. This is the common clock which you can see in this diagram. To apply the clock, clock is nothing but a high to low pulse you will be sending. You have to send high to low pulse to apply the clock to the 7 segment display interface for shifting in the bits. Okay, and which bit you are using to apply the clock? It is port 0 second bit. If you remember this diagram, coding will be easy. Okay, port 0.15 is used to send bit by bit the 8-bit data to display a character or a digit, and after sending each bit you need to apply clock. Okay, which bit is used to apply as I told, high to low pulse you have to send. First we need to send 1 through this pin, port 0.2, and then you are going to send 0 through this pin. Okay, so that is once you send high and once you send low, so that will be high to low clock pulse which clock in the data. Okay, this is what you have to do. So if I want to send a character, if I want to make a character or a digit get displayed onto the 7 segment display interface, how many clock pulses I have to apply? So since after each bit you are going to apply a clock pulse, it is totally 8 clock pulses required, okay, to display one character, one alphanumeric character. So if I want to display 4 digits or 4 characters in a 4-digit 7 segment display interface, how many clocks are required? So it is 8 into 4, 32 clocks are required. So this is what you need to know. So remember, we are going to send out the bits of the byte data bit by bit. Through which port you are sending? It is port 0.15. This is the port pin you are using to send out the data. And each of these port pins, they are to be configured as output ports. Remember, since we are sending out the data from LPC2148 microcontroller, we are sending out the data bit by bit to the 7 segment display interface. Just try to imagine the communication between LPC2148 and the 7 segment display interface. So you are having port 0 in LPC2148 microcontroller, and it should act as an output port to just send out the data bit by bit, and only one pin in port 0 is being used for the communication, that is port 0.50. So it is just serial communication, that is bit by bit the data is being sent out through port 0.15. So then after sending each bit in the byte data, we need to apply the clock. It should be high to low pulse that is sent. So that means port 0.2 is used to apply the common clock. And first we'll send out 1 on this particular port pin. Then we'll send out 0 on this pin. So this is how we are going to apply the clock. Okay, I'll show you how actually this is not there in your textbook or anywhere. Just to make you understand, I have prepared one slide. I hope you have understood to display 1, 2, 3, 4, in which order you have to send out the data. So these things you might have followed. So now in this diagram, I'll explain how actually the 7 after 8 clock pulses, how actually a character or a digit appears on the 7 segment display interface. So just see the tracing here. So this is the 7 segment code for 3, that is 0xB0. Okay, you know the 7 segment code, how actually it is constructed, all these are already explained. And we have taken H as the MSB and A as the LSB to construct this 7 segment code for 3. 10110000, this is the binary pattern. As I told, if you want to display 3 correctly on the 7 segment display interface, you need to send out the H bit first. Whether you take A as the MSB or H as the MSB, that doesn't matter. Always you have to send in this order the bits: H, G, F, E, D, C, P, A. So first, which bit we are sending? Just see the numbering here of the tracing. Send H bit first. So what is the status of H bit? It is 1. Since it is common anode type, we have assumed H bit will appear in at A position. So A segment, at this place H bit will appear. Since it is 1, that segment will not glow. Okay, we are sending first H bit. H bit will appear at A position, and since the status is 1, it will not glow. So next, which bit we have to send? Just see the second diagram. We have to send the 0 bit, that is the G bit. 0 means that segment will glow. So H bit gets shifted since we are using serial in parallel shift register, and we are applying clock pulse after each bit is sent out. So just observe, H bit will be shifted to B position and G bit will appear at A position. So G is glowing here. This segment is glowing. I have marked it in red color. Okay, next see the third diagram here. Next we have to send out F bit. And what is the status of F bit? It is 1. That means a H bit gets shifted to C position, G bit gets shifted to B position, which is glowing here. B segment is glowing, and F bit will be it will not be glowing. It is turned off. This segment is turned off since F bit status is 1. Okay, this is common anode type. So now after sending each bit, we need to apply the clock pulse so that the bits get shifted to the next segment. Okay. So now send E bit. What is the E bit status? It is 1. So H bit has been shifted to D position, G bit is shifted to C position, F bit is shifted to B position, and you can observe A bit is shifted to E bit is shifted to A position. So their status is 1. That means that's why these segments are not glowing. Only G bit is glowing till this. Okay. So coming to the next bit, we are sending D bit and we are applying the clock pulse. D bit status is 0. Once you apply the clock pulse, just observe H bit has been shifted to E position, right? And then G bit is shifted to D position, then F bit to the C position, E bit to B, and D bit is appearing in the A position. Okay, just see, since D bit status is 0, this segment is glowing. So now so far we have sent only 5 bits. Now 3 more bits are to be sent. So just see the sixth diagram here. We need to send C bit now. This is the order in which we are sending the bits. Now we are sending C bit and we are applying the clock pulse. So what happens? H bit will be shifted to next segment position. So H, G, F, E, D, C, B, A. Sorry, D, C, you just check the status. Since C value is 0, A segment will be glowing. Okay, A, D, G are the segments with value 0. So this is where they are positioned. So next see, after sending B bit in the seventh diagram, after sending B bit with status whose status is 0, just see what is the status in the 7 segment display interface. B bit will appear at A position. C bit has been shifted to B position. D bit is shifted to C position. See, one shift has taken place. Hope you are understanding. Okay. Finally, when I send the A bit and apply the 8th clock pulse, okay, after sending A bit and when I apply the 8th clock pulse, just observe A bit is appearing at A position itself, B bit is appearing at B, C, D. So they are into their places, and you can observe what is the character that has been displayed. See, character 3. We had constructed the 7 segment code B0H. After 8 clock pulses, we are observing character 3 displayed onto the 7 segment display interface. H gets shifted to this dot. We don't want dot to be displayed. That's why H segment status we have taken it as 1. Okay. Hope you have understood how actually internally 7 segment display interface works. So if I want to send one character or one digit onto the 7 segment display interface, I need to construct its 7 segment code, and I need to send out the bits one by one through port 0.15. That is the bit that is configured as an output port. So send out bit by bit the data to the 7 segment display interface, and after sending each bit, you have to apply the clock pulse. Through which port pin you are applying the clock pulse? It is port 0.2. Okay, the only these two pins you need to remember with respect to 7 segment display interface. Port 0.15 to send out the data bits, that is the 7 segment code what you have constructed, and H bit you have to send. This is the order in which you are going to send out H, G, F, E, D, C, B, A. Then to send, after sending each data bit, you need to apply the clock pulse, and which port pin you are using to apply the clock pulse? It is port 0.2. It is high to low pulse you have to send. That means we need to first send 1 over the port 0.2 pin, and then you need to send 0. So that will be that is nothing but applying clock to the 7 segment display interface. Okay, so this is what I wanted to tell, to show you how actually after applying 8 clock pulse the character appears on the 7 segment display interface. So now we shall discuss, with this knowledge, we shall discuss the first program of your lab syllabus. Okay. Develop an embedded C program. As I told, all Part B programs you are going to implement using C programming language. So this is the C program you need to implement to display the digits 0 to F using 7 segment display interface. Okay. You need to show the in scrolling fashion 0 to F. These characters are to be displayed in scrolling fashion. So how many iterations are required to display this? How actually we are deciding that, and how we are coding that in using C programming language, that we'll see. We need to include the header file. Say, for all Part B programs, you need to include the header file lpc214x.h. What you'll see in this header file is all the register definitions. Say you will be using IO set, IOSET. So for each registers, there will be addresses defined. We'll be just referring to those registers through their names. So whatever the registers you are using, their definitions you will be finding in lpc214x.h header file. So we'll be just using in those register names in our program. Okay. So coming to the first module, as since we don't want to have the function prototype statement, what I've done is first I've defined all the user defined functions, and at the end I've written the main function. Okay, so this is the function right segment for displaying an alphanumeric character on a 7-segment display interface. So we'll see what code we have used for displaying data on the 7-segment display interface. It is to display just one character or one digit. So this function is used to display a single character or a single digit on a 7-segment display interface. Okay, and if you are able to understand this code, any question given on 7-segment display interface, you'll be writing the same code. Write segment function remains the same. Since whatever may be the data, anyway we need to display character by character or digit by digit. So write segment code remains the same. So kindly analyze this whatever the code we have written for displaying a character or a digit onto the 7-segment display interface. Okay. So I have taken, just see, return type of the function, I've given it as void. This is the name of the function I've given, write segment. Again, it is left to your implementation, what name you want to give to the function. So to be more meaningful, I've used the function name as write segment. Since we are trying to write 8 segments, so that a character appears on the 7-segment display interface. And the one argument the function receives, unsigned char x. So what x holds? Can anyone guess? What x should hold? Yes. What x should hold? We are dealing with 7-segment display interface. What for this function is written? To display a character or a digit, that is alphabet or a digit, onto the 7-segment display interface. We are discussing this function. What x may hold or what x should hold? Can anyone quickly answer?
The digit that is going to be displayed.
Digit? What do you mean by digit? What is required for displaying anything onto the 7-segment display interface? Yes.
Hexadecimal digit.
What is that called as? 7-segment code, right? You cannot directly display one onto the 7-segment display interface. To display one, what is required? I need to construct 7-segment code. Are you getting? 7-segment code should be received by this variable x. While making a call to write segment function, in the calling function, I'll pass the 7-segment code of the character to be displayed. So that is received in the formal argument x. Are you getting? What x holds is the 7-segment code of the character or the digit to be displayed. Are you getting? So now within the function, I have declared a variable I, since it is acting as a loop control variable. Unsigned char I have taken, and this is how this is what the for loop header you are going to write. Why it is 0, I less than 8. Why 8? X holds the 7-segment code. Yeah, totally 8 bits I have to send. That means 7-segment code is an 1-byte code. I need to send bit by bit the data. So how many number of times the for loop has to be repeated? It is 8 times. Okay, so that's why the for loop header is running from, you can just observe the loop control variable I. It is running from 0 till 8. I equals to 0, I less than 8, I plus plus. Hope you have understood why we have written this for loop header. And why actually I is initialized to 0, that we will see within this for loop. Okay, we are not taking it as 1. We are taking I value as 0. This is the initial value of I we have taken, and it is running till 8, I less than 8, I plus plus. And you know which bit I have to send first? If you want to display, in which order you are sending the bits? Yes? What is the order of sending the bits? What is the order of sending the bits?
MSB to LSB.
No, don't tell MSB to LSB. It should not be MSB to LSB. Tell me the segment value. Which segment I have to send first? Which segment data?
H segment.
Yeah, don't tell MSB to LSB, since if you have constructed A as MSB and H as LSB, if you send A bit first, you'll not get the character expected on the 7-segment display interface. So if whenever, in whichever order you construct the 7-segment code, remember always you have to send H bit, then G, F, E, D, C, B, A. In this order only you have to send. Even though A as MSB have taken, LSB bit has to be sent first, then the next bit, and so on till the MSB bit. Since in our code, in our implementation, we have constructed the 7-segment code throughout, taking H as the MSB, then you can easily say that from MSB to LSB you are sending, since H as the MSB you have taken. So if it is asked from where to where you have to send the bits, it is H to A. H bit, whatever the 7-segment code you have constructed, see that H bit data is sent first, then G bit, F, E, T, C, D, A. Okay. And now I need to test. So you know that it is bit by bit data transfer. I need to test whether H bit in that 8 bit data or byte data, 7-segment code what you have constructed, whether that H bit is 1 or 0. How actually you can perform the test operation? You can use AND operation, right? Bitwise AND operation I can perform to test H bit whether it is 1 or 0. So how to test it? You know the logic. Already we have used in our program also. In ARM programming also we have done this. How actually we are performing test instruction I have used to test a bit whether it is 0 or 1. Test instruction you have used, right, which internally performs logical AND operation. So what is the value I have to take to perform AND operation? So only H bit I want to test whether it is 1 or 0. Whichever bit you want to test, take only that bit status as 1 and rest other bit status as 0. Are you getting? See 80H, how you got 80H? How actually you are getting 80H? I need to test only H bit. So whichever bit I want to test, I'll just take the value as 1 for that bit to perform AND operation. Rest other bits, I'll just perform AND with 0. So this is the data we are going to take to perform AND operation. So it is 8, 1,000 means it is 8, 000 means it is 0. 80H is the data for the first time. In the first iteration, 80H is the data we are taking to perform AND operation with the input data, that is the input variable which holds the 7-segment code. So how actually it works, I have also made the slide on that. We'll see in detail how this AND operation is taking place. Okay. So what happens in the first iteration? I is 0, okay, and we have parenthesized this expression. You have to parenthesize since AND operation is having higher priority over right shift operator. So whichever operation you want to perform first, just parenthesize here. 80H right shifted I times. I value is 0 here. That means for the first time, we'll perform AND operation with 80H itself. Since I want to test H bit, whether it is 0 or 1. If this results in 0, if you assume H bit was 1 in the input, in the 7-segment code what you have constructed, if H bit was 1, what will be the result of AND operation with 80H? Will it be 0 or non-zero value? Are you getting? If the 7-segment code what you have constructed, in that if H bit were to be 1 and you are performing AND operation with 80H, what will be the result of AND operation? Will it be 0 or non-zero? Yes. Will it be 0 or non-zero? Can anyone answer quickly? Are you following? Non-zero, right? If H bit is 1, so you are performing AND operation with 80H. MSB bit I want to test whether it is 0 or 1. If you perform AND operation with 80H, if that MSB bit was 1 in the input, performing AND with 1 will result in 1. Rest other bits we are performing AND with 0 means other bits will be 0. So you'll get a non-zero value as a result once you perform X and 80H. So if a non-zero means condition is satisfied, control will enter the if block where we are going to send 1. So after you come to know that the result of AND operation is resulting in non-zero value, which bit you have to send through port 0.15 is 1. Since that segment value is 1, we need to send out 1 through port 0.15. If this AND operation results in 0, you can infer that the bit in that input which you are testing, it is 0. So what we have to send is through port 0.15, 0 bit we have to send. So this if block, if else block, what we have written, it is to test whether the segment what you have taken, its status is 0 or 1. Okay. So see here what we are doing. We are using IO set register. IO set 0 equals 0x00008000. So why is this data we are writing to the IO set register? IO set 0 we have used since it is port 0 we are dealing with. So what for you are using IO set? If you want to output 1, okay, through a particular port pin, you'll be using IO set 0. And you know, only one bit in port 0 is used for sending out the data bits. It is port 0.15. So if you write 1 to the IO sets register, that means where that particular port pin status will be logic 1. You know this. 0 is insignificant. 0 is not having any effect on the port pins if you write 0 to the IO set 0 register. So since port 0.15, only that bit status must be 1, rest other bit status must be 0. So what will be that 32-bit value? It will be 00008000. This is what the data you'll send, you'll write to the IO set register, so that through port 0.15, 1 will be sent to the 7-segment display interface. We tested that bit. You know, in the first iteration, H bit is tested. After testing H bit, if H bit is 1, then control enters the if block and it writes this data to the IO set register, which sends 1 through port 0.15 to 7-segment display interface. If this AND operation results in 0, control will go to the else block where we are using IO clear register. To this register, you are writing the same data. Whether it is IO set or IO clear register you are using, if you want to send 1 through the particular port pin, you will write 1 to that appropriate bit in IO set register. If you want to send 0, then you are going to write in that position value 1. In IO clear register, will be writing 1. In IO set register, will be writing 1 to send 1. In IO clear register, will be just giving the data as 1 to send 0 to that particular port pin. Okay, so that I've shown in this diagram. You can see. So bit 15, just observe rest other bit values I've taken it as 0. Since port 0.15 is used for communication between LPC 2148 and 7-segment display interface, only this bit status we have taken it as 1. So what is this 32-bit value you are going to get? 00008000. So this is what the data you are going to get. Okay. So to which register we have to write this data to send out 1? It is IO set register. If you want to send out 0 to 0 as the bit status to the 7-segment display interface, same value will be writing to IO clear register. Okay. Are you getting? Have you understood what we are writing in IO set 0 and IO clear 0 register? It is 40 followed by that 8 followed by 3 zeros. Just observe bit 15. That only is having the value 1. So this way, if you write this data into the IO set register, what it means is we are sending 1 through port 0.15. If the same data is written to IO clear register, then what is the meaning is the bit 0, that is port 0.15. Through this bit, we are sending 0. You know the purpose of IO set and IO clear register. To make the pin status logic 1 or logic 0, we are using IO set, IO clear registers respectively. What is the data we are writing is 0 is not having any effect either in set 0 register or clear 0 register. So whichever, that is, if you want to send out 1, we'll be using IO set register. If you want to send out 0, you'll be using IO clear register. After sending either 1 or 0, you need to apply the clock. Which port pin is used to apply the clock? It is port 0.2, right? That is used to apply the clock. You know how to apply the clock? It is high to low pulse you are sending. So first you are sending 1 through port 0.2 and then 0. So port 0.2, only this pin has to be 1. Can you tell me the 32-bit data which you have to send or which you have to write? What is the 32-bit data I have to write? Only bit 2 is to be 1. High to low pulse I have to send. I need to write to IO set register. Okay. Can anyone tell? Yes. To IO set register, what value I have to write? To apply the clock pulse, I need to send first 1, then 0. P0.2 is the port pin. That means bit 2. What value I have to write to bit 2? Are you all following? Can you tell what value I have to write to bit 2? No one wants to answer? Yes. No one wants to answer? It's it's getting late. Can anyone answer quickly? If you don't know, at least tell don't know. Am I audible? Did you got the question? You need to apply a high to low clock pulse. After each bit is sent, you need to apply a high to low clock pulse. 1 and 0. Okay. Through which pin you are applying the high to low clock pulses? Port 0.2. So bit 2 status must be what? What data I have to write to IO set register? First I'll send 1 and then I'll send 0. I need to write the data to IO set 0 register and IO clear 0 register. Are you getting? What I have to write? What is the value I have to write to these? IO clear. It is not IO set, it is IO clear. Can anyone tell what value, what 32-bit value I need to write to IO clear register and IO set register? First, I need to write to IO set.
0804, ma'am. When zeros
Yeah,
follow.
4 zeros followed by 4, correct? So, sorry, 00 here. Just see here. So, what is the value we are writing? Only least significant nibble will be 4, right? That is this 4 bits. It is 0100. Only B2 bit will be 1. Rest all bits will be 0. So, what is that 32-bit value will get? All zeros. Least significant hex digit will be 0. Just see. I was set 0. To this we are writing 0x all 0 4. And IO clear. After sending high pulse, I need to send a low pulse. Where we'll send IO clear 0 equals 0x all 0 4. Close the for loop and close the function. How many times this for loop is executed? 8 times. And if condition is written to test whether a particular bit is 0 or 1. If you find that the bit is 1, we'll write to IO set register to send 1, interpreting the bit to be sent as 1. So if it were to be 0, then we'll write to IO clear register to send out 0. After sending either 1 or 0, we need to apply a high to low clock pulse by through port 0.2 bit. We'll write 1 to IO set register in that the bit position 2, and similarly we'll write at the bit position 2 1 to the IO clear register. Same data is to be written to IO set register and IO clear register. So this is how you're applying the clock. So next I gets incremented. I will be incremented to 1. 1 is less than 8. Condition is satisfied. Control enters. So first we are shifting, right shifting 80H one time. When you right shift 80H one time, what will be the data? It will be 40H. That means what we are doing is we are trying to test now G bit. H bit, to test H bit, we have taken 80H as the data, mask data. To test G bit, only one we need to take at G bit position and rest other bit status must be 0. When 80H right shifted one time, what you'll get is 40H. That is the data you are taking to perform the mask operation or AND operation. For that, the result of AND operation, with that we can infer whether we need to send 1 or 0. Okay, in the next iteration. So this process is repeated. So after all the 8 iteration, what you'll see is the whatever the character or the 7 segment code you are having in that variable x, so that particular character will be displayed onto the 7 segment display interface. Okay, you see I've illustrated in this diagram. So assume I want to display 0. 7 segment code for 0 it is C0. 1 1 0 0. You can see only G bit should not glow. G and H bit should not glow. So this is the 7 segment code C0H, and this is what is held in X variable. Initially I is 0. We are testing whether 0 is less than 8. Yes, it is true. And this is the code C0H we have taken. That is the 8-bit code. And you can see in the first iteration we are performing AND operation with 80H. 80H you are performing, and the result of AND operation is, see, non-zero value you have got after AND operation is performed. Once you get non-zero, what you can infer? H bit is 1. This is what the inference you can make upon performing AND operation. So now what we'll do is we'll send out 1. Controller will enter the if block and it sends out 1 by writing to the IO set register. 1 is written. So in the next iteration, what happened? And after that, we need to apply the clock pulse, high to low clock pulse. Then next we need to test G bit. What we are doing in the next iteration, I value will be 1. 1 is less than 8, condition is satisfied. Control enter the loop for the second time, where we are performing AND operation with what value? 40H. Whichever bit I want to test, only I'll perform AND operation with 1. Rest of the bit status I'll take it as 0. 80H right shifted I times. Here I value is 1. What is the value you'll get? Mask value, it is 40H. If you perform AND operation with this value, what you'll get is 01000000. This is again a non-zero value. If you get the result of AND operation as non-zero value, we can infer that G bit is 1. So send out that 1 status through port 0.15. In the next iteration, I value will be 2. Okay. And now 80H right shifted 2 times. What will be the value? It will be 20H, right? That means which bit we need to test now in the third iteration? F bit. Now, if you perform AND, just see F bit status is 0. If you perform AND operation with 20H, what it results in? It is all zeros. So with 0 result, what we can infer? F bit status is 0. So what we are going to do is, condition will be failure in the if condition. Control will go to the else block, where we are writing to the IO clear register a value 1 at this position, so that 0 will be sent out through port 0.15. Same process is repeated. In the next iteration, I value will be 3. 80H right shifted 3 times, it results in 10H. This is the mask value we are taking to perform AND operation. After performing AND, it is again resulted in 0. We can infer that E bit which we are testing, it is 0. So just write to IO clear register the data, that is at port 0. That is 15. You write the data as 1. Okay. So that 0 will be sent out through this particular port pin. Same process is repeated for sending the other for testing other 4 bits. I've shown for only 4 bits. Same thing is repeated for other 4 bits. Have you all followed? Are you able to follow?
Yes, ma'am.
Yes, ma'am.
Okay. If you want, I'll discuss again. If you are having any doubt, kindly go through it. I'll share the material. You just kindly go through it. We'll again discuss in the next class. Okay. Let me stop here since faculty may be waiting. Yes, we'll stop here. Thank you.